Okay, we've talked about conservative forces. Conservative force is basically the total amount work done is zero if you come back to the same location. So gravity's like that. If I do this, the work that gravity did, negative work as I went up, right, because gravity's down, positive work there, and if you add all those things up, they're linear, it's all easy, and it ends up being zero when it comes back to the same direction. I was checking something in the, okay, doesn't matter. Okay, we've talked about conservative forces. A conservative force is a force that in a round trip, when you come back to the same location, that force has done zero work. So gravity is a good example of that. If I start here, do this, gravity just did negative work, right? Because the motion was in the opposite direction from gravity. Now it does some positive work. Now it's doing negative work. Since the work done by gravity is linear, it turns out that the positives and the negatives balance out, and the total work done by gravity is zero. In fact, total work done by gravity, zero. So that's a conservative force. A spring is another conservative force that we'll talk about later. And one good thing about conservative forces is we can kind of take the work-energy relationship, delta K is equal to the work done, and we can take the conservative forces and kind of bring them over here and think of the system as a little broader, and it makes it a little easier to solve a lot of problems. I'm going to show you how we do that. We do that using a concept called potential energy. And potential energy, particularly for gravity, it's almost a fake energy. It's just a bookmark, a way we have of representing the work done by, in this case, we'll talk about gravity, in a simpler way. So you don't have to do as much math. Let's take a look at this. We've got a ball dropped. A ball dropped, mg delta y, they're in the same direction, cosine is zero, so that is the work done by gravity. Okay? If we come over here, a block that slides down a ramp, mg delta x times the cosine of the angle in between, okay, is going to be the work done by gravity. But look what happens if you look at this delta x, if you group these together, delta x times the cosine of this angle actually just gives you the change in the y dimension. I hate that this is the x dimension. The change in the vertical dimension, which I'm just going to call delta y. So guess what? mg delta y. So as that block goes down the ramp, I don't even need to know the delta x. All I need to do is know how far the block went down, and I've got my delta y and mg delta y. Look, mg delta y. Hey, here's a guy, he's throwing a javelin. I don't know if it's a guy. Someone's throwing a javelin and the moves in this direction. This is a little trickier because mg is down, cosine of that angle, mg delta x cosine of that angle, but that's the same as negative the cosine of that angle, and again, this times the cosine of that would give you delta y, a change in the height. I don't love that I'm using delta x here and delta x here. It's not horizontal and vertical, but the change in the height is given by this times the cosine of this angle, which is the negative of this, so it ends up being negative mg delta y. So you're seeing this mg delta y, mg, oh, I forgot my negative, mg delta y, mg delta y. So the work done by gravity is related to the change in height. And in fact, if we say change in height, this would be a negative number. This would be a positive number. So we can say work done by gravity is equal to negative mg times the change in height. Okay? That's really nice. And the reason that's really nice is because now I don't have to do all my fingers and the angle and oh my God, that takes so long. I don't have to do that. I can replace all these problems. I can replace the work done by gravity by just this. Now let's see how that works with the work-energy relationship. Okay. The work-energy relationship tells me that the total work is equal to the change in kinetic energy of the object. And we've done a whole lot of stuff where we've had objects and then we've looked at them as systems. And this is another one of those ones where we're going to be doing that. So the total work on an object, let's say, is work done by friction plus work done by the applied force, if there's something pushing on it, plus work done by gravity, plus work done. I could list all the different things that are doing work on an object, right? And that's going to be equal to the change in K. Now, look at this. Okay, this is negative mgh is the work done by gravity. So let me do that. Instead of that, I'm going to make it mg delta h. Okay. If I add that to both sides, what I get is, I'll just say sum of work from other sources equals mgh, mg times the change in height, plus the change in kinetic energy. And in fact, we use this so often that we give this a special name. And it's kind of a fake again. We call it potential energy. Change in potential energy. And in fact, this is the change in gravitational potential energy, which we're going to call delta U with a little g. So that's potential energy, gravitational potential energy, change in gravitational potential energy. Okay, so really what happens is work adds energy to a system. Okay, work from external sources add energy to a system. What's the system in this case? I mean, really it's just this object, right? No, because this potential energy depends on this object in relation to the Earth in most of our cases. It could be in relation to another planet, but in this case we're going to be talking about the Earth. Okay, so change in potential energy plus change in kinetic energy equals the amount of work that's put in. But there's something that's even a little easier, and then I will get a little more into that equation. If this work is zero, okay, so for an isolated system, and I'll talk about what that isolated system is, then no work is being done on it, then this delta U plus delta K is zero. That means that any change in delta U has to be reflected, any increase in delta U, in potential energy, has to be reflected by a decrease in kinetic. Any decrease in potential would correspond to an increase in potential. And all of that whole thing comes down to, we could say the change in, let's rewrite that very quickly, and I'm going to have to get a different pen out. Okay, so 0 equals U final, I'm going to leave out the G for now. U final, let me call it U final, U prime, the potential energy at the end of a problem minus the potential energy at the beginning of a problem, plus K prime minus K. All I did is substitute delta. I'm using prime at the end, at the beginning, rather than little zeros there. Okay. Well, if we group these up, if we add U and K to both sides, what we get is U plus K equals U prime plus K prime. And this is called conservation of total mechanical energy. The potential plus the kinetics will always add up to the same thing in an isolated system. Now, our isolated system, I need to talk a little bit about what potential energy means, how we calculate it. It's related to that. And we need to talk about what the system is. And that's something we'll do in the next video.